In chapter 14, we're going to start talking about vector valued functions. So much of this will be similar to what we talked about before, but instead of talking about vector equations, we're now going to talk about vector functions. So when we talk about a vector valued function, and it would be r of t equal to components x of t, y of t, z of t, we view it in two different ways. It could be a set of parametric equations. Notice we have the parametric equations x, y, and z of t. But we can also look at it as just one single function r of t, which we call a vector valued function because it describes a function in terms of vectors. Oftentimes we'll just say vector function. So this function will just vary with respect to the independent variable t. So for example, if I had the unit circle, I could write it as x equals to cosine t, y is equal to sine of t, where z value is equal to 0, because here I'm just talking about space, three-dimensional space. So that would give me the unit circle in the xy plane. But I could also write it as the vector function r of t as the vector cosine sine 0. So this is the idea. For any curve in space, we can describe the curve as a vector valued function. Now we were using x, y, and z previously, but that's just variables. We can also use f, g, and h. Since this is a vector function, that means each component is also a function of t. Or we can write it in terms of the unit vectors I, j, and k. So any curve in space can be described as a vector valued function r, where when you look at the graph, any point on this graph can correspond to a vector where the head of the vector describes this point. So if you look at this curve, at every point on this curve, we can describe that point in terms of a vector whose head is the vector at that point. So as our t values go on in this particular example, it looks like our curve is generated from left to right. So remember in parametric equations, we talked about a positive orientation, and that would be the direction that your curve is generated as your t values get larger and larger and larger. So what we didn't talk about before was this idea of a domain. But now that we're talking about functions, it makes sense for us to talk about the domain of our function r. So since r is in components, f, g, and h, or you could say x, y, z, doesn't really matter, each one of those components is going to have a domain. So the domain of r is simply the intersection of the domain of each one of those components. So it's the t values that they have in common. Again, a lot of these examples are going to be similar because we looked at these in previous sections, but again, in the previous sections, we were talking about this in terms of an equation, not as a function. So going back to previous section, let's say in example 1, we wanted to find a vector function for the line that passes through these 2 points. P is 2, 1, negative 4, Q is 3, 0, negative 6. And then I added to it, so we did this before in previous sections, state the domain. Okay, well first let's go ahead and write the equation of this line in vector form. We need our direction vector, which would simply be the direction, or PQ, or you could do QP. Remember, there's no direction here. So that would be Q minus P, so 3 minus 2 would be the vector 1. 0 minus 1 would be negative 1. And then negative 6 minus a negative 4 should be a negative 2. So we have our direction vector, and I'm going to use the point P as going back to previous section, that would be your x sub 0, y sub 0, z sub 0. That gives me my vector valued function r of the point 2, 1, negative 4 plus t times the direction vector 1, negative 2. So instead of keeping it separated, I'm going to bring this together and write it as a single function. It would be 2 plus t, comma 1 minus t, comma negative 4 minus 2t. So this would be my vector valued function, or I could simply write it parametrically as, maybe I'll put that off to the side. I could write that as x equal to, and I could do x of t, right? Equal to 2 plus t, y of t equal to 1 minus t, and z of t equal to negative 4 minus 2t. So those are the two ways that we look at this. Now, what about the domain? So the domain of R is going to be looking at each one of these pieces, the X, the Y, and the Z, or you can call it FGH, and figuring out the domain of each of those pieces. Well, if we look at X of t, it's 2 plus t. 2 plus t. Do I have any restrictions, or can I put in any t value? And the answer is yes. So all real numbers in interval notation, that would be negative infinity to positive infinity. If we look at 1 minus t, no restriction. I could put any t value I want from negative infinity to positive infinity. And it'll be the last one as well. Negative infinity to positive infinity would be the domain. So the domain of R is the intersection of all three. And I'll just write DOM for domain and parentheses R. This is my own notation. So the domain of R is going to be negative infinity to positive infinity. So again, the idea is you look at each one of those pieces, figure out the domain for each piece, and then look at their intersection. Let's do another example. In example 2, we want to find the domain of this function. It's natural log of ti plus square root of 4 minus tj plus 1 over t minus 4k. So this is written in terms of the ijk form, which is fine. If I look at the natural log, and I could call this xyz, I could call this fgh, doesn't matter to me, it's just notation. If I look at, oh, maybe I'll write it all out, the domain of f, this is the natural log function. So remember, the natural log function is only defined for positive values. It's undefined for 0 and negative values. So the domain of natural log of t is the interval from 0 to infinity with parentheses. And the domain of g, which is the square root function, remember the square root function can never be negative. So what I'm doing here is I'm taking 4 minus t and I'm making sure that it's greater than or equal to 0, which means that my t values have to be less than or equal to 4. That would be the interval from negative infinity to 4. I can include 4, so I'm going to use a bracket. And then the last piece, h, that's a fraction. Fractions are undefined where the denominator is equal to 0. So I notice that t cannot be equal to 4, because if t is equal to 4, 1 over t minus 4 is undefined. So I could put in any t value except 4, which means in interval notation I could use anything from negative infinity to 4, parentheses, and then we use our set notation u for union, parentheses 4 to positive infinity. So these are the domains for each of those three components. Now the domain for R is what they have in common. The domain of R is going to be parentheses 0 to 4, and that's it. Okay, if you don't see that, go ahead and draw yourself a number line. Look at all the numbers that show up in the 3 domains, and I see a 0, I see a 4. So again, this is not to scale. So I'll put 0 and 4 on my number line. If I look at the domain of f, that goes from 0 to positive infinity. So maybe I'll use red here. So at 0, it's undefined, so I'm going to use an open circle, and then everything to positive infinity. So that would be the domain of f. G is negative infinity to 4, and I can include 4. Oops, so that would be G. H is everything except 4, so open circle at 4. And the domain is where all of these overlap. So you see they only overlap from 0 to 4, and we don't include 4 because we have an open circle there. Now, something else that may come up in this section is the use of technology to graph some odd shapes. If you don't have this technology, I'll just do one example here. And this would be of a spiral, or sometimes called a helix. This comes up a lot in physics when you're dealing with springs. In example 3, it says to find the domain of the function. So no problem, we can do that. And then describe its graph. So I'm going to do this without a graphing utility, but please feel free in this section to use graphing utilities as much as you want. So if we're going to find the domain of our function r, we look at all 3 pieces. And I could see that with cosine, the domain is all real numbers, no restriction there. So negative infinity to positive infinity. Sine, negative infinity to positive infinity. And then when you look at t over pi, I can put in any value for t. So again, it's negative to positive infinity. I have the domain of my function r as negative to positive infinity. Now I'm going to graph this. Again, please use a graphing utility. If you do have a 3D grapher, that's awesome. If you don't, what you might want to do is notice that the first 2 components, and I'm going to view this as an x, a y, and a z. X and y, we have a cosine and a sine. So that tells me that if z is not there, and I'm just looking at x and y, then I probably have something circular or elliptical probably, because it's a 3 cosine and a 2 sine. So it's probably an ellipse. I'm going to go ahead and graph this. With x and y. And here I'm just looking at z equal to 0 and seeing what the graph would be in the xy plane. So if t is 0, then cosine of 0 is 1, and I'm at 3. But sine of 0 is 0, so it's going to be the 0.30. Let's go to t equal to pi over 2. So at pi over 2, cosine of pi over 2 is 0, but sine of pi over 2 is 1, so I'm at 2. And then let's go to pi. That would be negative 3 for my x value. My y value is 0. And then at 3 pi over 2, I'm at negative 2. I could see that this is an ellipse in the xy plane. And although it's not required, I can even find the equation of this ellipse. The equation is going to be x squared over 9 plus y squared over 4 equal to 1. Okay, going back to those conic sections that we looked at previously. So now look at the z value. As t values get larger and larger and larger, so does the z value. As the t values get smaller and smaller and we're going in the negative direction, the z values go down in the negative direction. So if I were to graph this by hand, again, it's not required that you graph it by hand. However, if I were, to graph this by hand, I would first graph that initial, maybe I'll do some dotted lines, that initial curve that we looked at, that ellipse. Remember, it's wider on the X and smaller on the Y. And then as the t values get larger and larger and larger, the z values get larger and larger and larger, but these x and y's will always be elliptical shape. So again, sorry about the hand drawing. So we get this spring going up, and it is generated upwards. As the t values get smaller and smaller and smaller, it's still elliptical, but we're going, oh my gosh, that drawing is terrible, but we're going down. So that might come up in this section as well, where you're asked to graph some sort of weird shape. If you're not sure and you don't have a graphing utility, just look at the XY plane and then imagine what happens as your Z values change. We're talking about functions. Something else that comes up when we talk about functions is this idea of limits and continuity. Limits, when we talk about vector valued function, is similar to limits from calculus 1. But you have to remember that since our function is a vector valued function, our limit is also a vector. So we're looking at a vector that we're approaching. So here, the definition just says that the limit of our vector valued function, the limit of our vector valued function as t approaches some value is going to be the vector L, provided that, now this is similar to the absolute value of f of x minus L, but it's in vectors. So provided that when you do take this limit of the vector valued function minus the limit vector, that you get 0. So a little bit different. There's no epsilon delta like we do when we talk about limits in the usual sense, because those are not vector valued functions in calculus 1. So those are just real valued functions. So the limit is a real value. So let's say that we do have this vector value function r. And here I've written it in terms of f, g, and h. Or you could write it in terms of the unit vectors I, j, k. To figure out the limit, all you have to do is take the limit of each component. If the limit exists for each component, then that's the limit written as a vector. So that's really important. It's a vector that we're approaching. Now, if even one of those limits does not exist, then the limit of r does not exist. So in order for the limit of r to exist, all 3 pieces has to have a limit that exists. Although this is not, you're not doing questions on this in this section for your MyLab, we should talk about continuity because that follows from limits. So a function is continuous, a vector valued function is continuous, provided that the limit is equal to the vector at A. So when you look at all the 3 components, the 3 components, f, g, and h, they're continuous if and only if r is continuous. Or in other words, r is continuous if and only if f, g, and h is continuous. So in order for it to be continuous, which is really important, because normally when we talk about these vector valued functions, we typically are talking about an object moving through space for some time t. So it's really important that the path of this object does not break, that it is a continuous path. Let's go back to that diagram we had in the beginning. Let's just say that I wanted to look at, maybe I'll do a nice big dot here. I wanted to look at to see if the limit exists at this point on the curve. If the limit exists, then I should be able to approach the vector that corresponds to that point. So it has to be defined for it to be continuous, but it doesn't have to be defined. It still has to be defined for the limit to exist as well, in this particular case when we're talking about vector valued functions. So does it? Yeah, sure. I can get closer and closer and closer and closer to this vector, and as close as I want, which means that the limit does exist. So it's the same idea. Can we get as close as we want to that vector? Yes, the limit exists. Now, when you evaluate the limit, it's fairly straightforward. In example 4, we're going to evaluate the limit as t approaches pi over 2 of our vector valued function r of t, which is 3 cosine ti plus 2 sine tj plus 7k. That just means that we're going to take the limit of each piece. Now you can write it as the vector because it is going to be a vector, where you take the limit as t approaches pi over 2 for each piece. The first piece is 3 cosine of t, comma, because I'm writing it as a vector, or you could keep it in ijk form. The limit as t approaches pi over 2 of 2 sine t, comma, the limit as t approaches pi over 2 of 7. Notice that I left off the ijk because I'm writing it with those vector brackets. And this is a plug in the value, see if you get a number. If you do, you're golden, you're done. So cosine of pi over 2 is simply 0, so this is 0, comma, the limit of 2 sine t as t approaches pi over 2 is going to be sine of pi over 2 is 1, so this is 2. And then the last one, the limit of a constant is the constant. This is just 7. So that's our limit. It's the vector 0, 2, 7. That's the vector we're approaching as t approaches pi over 2. Again, you can write it in the ijk form if you like as well. So the first component is 0, so this would simply be 2j plus 7k. And the last two examples for this section, this is a really short section. Let's evaluate this limit here as t goes to infinity. So although there are not parentheses around this, you can assume that this is the limit of this whole expression. So let's say I did want to keep this in the ijk form. I didn't want to write it with those vector brackets. Well, if I do that, then I have to take the limit as t goes to infinity of e to the negative t. I have to keep the I vector on there, right? Because previously I figured out the limit and I kept the vector brackets on there. Here, if I don't use those vector brackets, I have to keep the ijk because it's a vector. Plus the limit as t goes to infinity, of t over 2t minus 7j plus the limit as t goes to infinity of 7k. So I figure out each one of those limits. Now the first one, it's easier for me to see if I get rid of the negative exponent and write this as 1 over e to the t, I. Now I can see as t goes to infinity, that denominator is just growing huge. So the whole fraction, 1 over infinity, is actually approaching 0. In this second limit, if I plug in infinity, I get infinity over infinity, which is an indeterminate form. So just as a review, infinity over infinity, and it could be plus or minus. 0 over 0, 1 to the infinity, 0 to the 0 power, 0 to infinity, infinity minus infinity. These are all indeterminate forms. An indeterminate does not mean the limit does not exist. It means you got to do something else because we cannot determine the limit because it's an indeterminate form. So here I have two choices. Since I got an infinity over infinity, I can use L'Hopital's rule, take the derivative in the numerator and denominator, or I could simply divide top and bottom by t, and this can be written as 1 over 2, which is what I'm going to do, minus 7 over t. And then the limit of a constant is a constant, so the limit here is just going to be 7k. All right, so this is going to be 0, I plus, as t goes to infinity, the 7 over t goes to 0, so this is just 1/2 j plus 7k. So I didn't have to keep the 0 on there. Or you could write it in vector form as a vector 0, 1/2, 7. All right. Something else that might come up in this section is finding the intersection of different curves. In example 6, I have y equals to 16. That's a plane. It's not a line because we're in three-dimensional space now. And then r of t is a line in vector form. So since my first equation says y equal to 16, I'm going to write my r as x, y, z. So in order for these two to intersect or be equal to, points that they are equal to each other, and they may not. They may be parallel, they may intersect in one point, they may intersect in infinitely many points. I don't know. What I have to do is I have to set them equal to each other. I do know that y is equal to 16, so I could simply plug that in for the y component and solve that equation, which would be 4 plus 3t equal to 16. So if they do intersect, their y values have to be the same. So we have 3t is equal to 12, t is equal to 4. So that also tells me that these are going to intersect when t is equal to 4. So to figure out the x and the z values, all I have to do is plug in 4 for t. So if t is equal to 4, then it's going to be 8, 16 I already had, and then putting in 4 for t, I get negative 24. So that's the vector. Oops, so sorry. So that's in vector form, but we're asked for a point. So the point where these intersect is the point 8, 16, negative 24. So if this is a plane and a line, then that tells me the line R is passing through that plane at the point 8, 16, negative 24. Okay, that's it for this section.